Hello once again, my dear students. So for this lesson, let's start it with a puzzle. A puzzle that was posed some time ago goes something like this. Three utility companies need or each need to run pipes to three houses. Can they do so without crossing over each other's pipes at any point? The puzzle is illustrated in the figure. Go ahead and try to draw pipes connecting its utility company to its house without letting any pipes cross over each other. So as you can see here, we have the houses X, Y, Z. So those are the vertices here, X, Y, Z. And then you have the utility companies here, A, B, C. So you have there. So it means here that its utility company has to run pipes to each of the three houses, and that's actually the edges here. So what you're going to do is to actually avoid the crossing over of the pipes here. So you need to move this so that it will not cross over this line here. So you need to actually just like intersection, but these are not intersection, it's actually crossing over. So can we avoid that? So to answer this problem, we need to have actually an idea or concept, okay? And there's a concept of math behind this problem. And that's what we're going to discuss for today. It's all about planar graph. So what is a planar graph? A planar graph is a graph that can be drawn so that no edges intersect each other except at the vertices. Okay, let's have some examples of planar graph. Is this a planar graph? This one? Yes. Why? Because we can actually move this line here. We can stretch we can stretch it to like this one so that there will be no crossover or there will be no intersection of lines or edges. Okay, and then these two graphs are still similar or the same. As we learned before, that a graph are equivalent if they have the same way of connecting the lines and the points or the vertices. It's how they are related or connected that matters. Okay, so these are similar. So it's a planar because you can make or you can actually have an equivalent graph wherein there will be no intersecting or crossing over of lines. How about this graph here? Can we actually draw an equivalent equivalent graph, equivalent graph such that there will be no crossing over of lines or intersecting of lines. So in here, we can actually move, okay, or you can actually put these lines in another part of the graph so that there will be no overlapping here of lines or crossing over of lines here. We can avoid the intersection here, so you can stretch this line from A to D. You can stretch that and you put it outside that part of this graph here, and this line connecting B and D, you can stretch that and put it outside, so that is the line. And therefore, as you can see here, there will be no more intersecting lines or overlapping lines, or what we call crossing over of lines. Therefore, the original graph here, this graph is called planar because there is an equivalent graph wherein we can actually write it as without overlapping lines or intersecting lines in the graph. So that's this one. This original graph here, the given graph, is actually planar graph. So that's the meaning of planar. Okay, so let's try some other figures here. Okay, so in here we need to actually change this, or we have to connect these points such that it will not overlap this line here. So we can actually change this line. We can actually put it here connecting 2 points, so just the same, okay, with the graph. And this line, so that there will be no intersection here anymore, you can actually connect the 2 points by doing this. Okay, so removing this line here, and there will be no intersection, so the graph will become like this one, okay, that one. So as you can see, without these two here, it's actually this one. These are the lines already, therefore there are no more intersecting lines, and we can say that the original graph here is a planar graph. How about this? Okay, so we can actually move this line here, move this line connecting these 2 points. We can actually put it here so that there will be no intersecting here, so that's already fine. How about this line? So we can actually move this line here so that there will be no intersecting here. So we move this line to this point, so it connects the 2 points here, so just the same. The problem now is this line here, this one. So it is still intersect this, so we need to avoid this one, okay, because we did not actually expand move this one. So we need to move this part here. So if we are going to move that, so it will be outside here, but there's a problem. If you connect it to that point, there will be intersection here. So is there another way? So you think of another line to move, okay, such that there will be no more intersection. But in this case, it's not planar. It's impossible to make it actually a graph without intersecting lines. So this graph here, the original graph, is not a planar graph. So this one is not a planar graph. How about this one? Is it a planar graph? So as you can see, there are many intersecting lines, but can we avoid it? Can we make an equivalent graph such that there will be no more intersecting lines? So this line here, we can remove this, and we can actually connect the 2 lines, the 2 points still, by using this line instead of this. And the only problem is this one and with that one. Okay, so we can actually move, okay, this point, because it's an equivalent graph, isn't it? So we can actually transfer this point to this point, for example, and isn't it this point A, for example, is being transposed here, and that A should be connected to this point with this line. So that line becomes this line here becomes this line, and then this line here becomes this line. So we remove this already, and then we also remove this line here, that is the line. So the original the remaining lines are, it's here, the other one is here, and then you have this one, and then this one. So as you can see, the red is actually the equivalent graph of the blue, okay, and in the red there is no more intersecting lines, and it becomes planar. So the original graph is considered a planar graph. Okay, so going back to the problem a while ago I presented, can we actually make it planar or show it as planar? If you're going to try this and you move all the lines here so that there will be no more intersecting, or what we call without crossing over of pipes here, is it possible? So you may actually answer this, okay, solve this one, but the answer here is you cannot. You cannot, okay. You have to try it and show it that you cannot actually make an equivalent graph such that there will be no crossing over of pipes. The application of that concept, the planar graph, okay, is on map coloring maps. In the mid-1800s, Francis Guthrie was trying to color a map of the counties of England so that it would be easy to distinguish the countries. He wanted counties or counties, I'm sorry. He wanted counties sharing a common border to have different colors. After several attempts, he noticed that 4 colors were required to color the map, but no more. This observation became known as the 4-color problem. Let's have an example of that. Here is a map of the contiguous states of the United States of America colored similarly. Note that the map has only 4 colors, and then no 2 states that share a common border have the same color. Okay, so to color a map, it means here for the 4-color theorem or problem, we just need at most 4 colors, such that okay, there will be no states, okay, or no town if these are towns, okay, no towns with common border which are of the same color. Okay, so that you can distinguish one town from the other. So there will be no two towns with the same color with common border. So those with common border should have different color to distinguish one from the other. Okay, so let's say for example there's a map, okay, and then how to convert the map to a graph. So if the first thing is this A, B, C here, for example, are name of towns or cities. Okay, so you have the name of the towns here or cities. Then the boundary actually tells us about a line. So if there is a boundary between 2 cities, you need to connect them. So let's say A and B has a boundary, this one, so you connect A and B. A is also has a boundary with G, so you connect that A with G. Okay, so B has a boundary with C, so you connect that with C, and C has a boundary with D, so you connect that. There is also a boundary with B here, so you connect, that's one pointer. And then C has a boundary with E, so you connect it with E. E has a boundary with F, and F has a boundary with G, and it has also a boundary with B. So that's actually the converted graph of this map. Okay, so you have it there. Okay, I'm sorry, this point here, there's no boundary. So parang isang point lang yon na ano. So dito tingnan mo, wala siya. Okay, so wala siya. Okay, sorry for that. Now, so that's a converted graph. This is the graph. And then let's have another. Okay, let's say for example this is a map and you want to color it. What should be the minimum number of colors that you need to use so that there will be no neighboring towns or neighboring places with common colors, so that you can actually distinguish? And what's the minimum number of colors to be used? Is it 2, is it 3, or 4? It says there in the 4-color theorem, you may have at most 4. So pwedeng 4, pwedeng 3, pwedeng 2. Okay, so if the graph should be planar, okay, should be planar. So it says here, the fictional map below shows the boundaries of countries and a rectangular continent. Represent the map as a graph and find a coloring of the graph using the fewest possible color or number of colors. Okay, as I said, it may be 4, it may be 3, or maybe just 2. You just need 2 different colors. Then color them up according to the graph coloring. Okay, so the first thing to do is you may actually name, okay, the countries. So sorry, these are countries, it says here. And we have here, let's say for example, A, and then you can actually take this as B, and then this as C, D, this is E, this is F, for example, this is G, this is H, this is HI, then this is J. So this one is still part of E, okay? And then these are actually the vertices, okay? So you can have a point here for the vertices and then those letters are just the names, no? Okay, so if there's a boundary for that, you need to connect them. So A has a boundary with B, connect those 2 points. A, it has a boundary with H. Then A also has a boundary with J. Then you go to B, it has a boundary with H, a boundary with G, it has a boundary with C. Okay, no more. So we go to C, has a boundary with G, it has a boundary with D, and D has a boundary with E. Okay, then E has a boundary with G, and E also has a boundary with F. And then I has a boundary with it's inside H, so it has a boundary with H. And then H has a boundary with G here. And then H also has a boundary with E, as you can see there. So you need to connect those 2 points. Is I has a boundary with F? Okay, no. If H has a boundary with F, no. And is E has a boundary with J? Yes, this part here. So you can connect J and E here. Okay, and J is also has a boundary with that of H. So you connect J and H. And that is actually the planar graph of this map. Okay, so as you can see, there's no intersecting line, so that's why it's a planar. And you can actually use the 4-color theorem here, that the most number of color is 4, but maybe we can find less than 4. It can be 3 or 2. Okay, so to find it, so this is the converted, okay, graph a while ago. That's how we did it a while ago. So this is the graph, and then how to get, okay, or to determine the color. So you may choose, okay, any color you want. Okay, you may start at any point here. You may start with this point here. Let's say this point is this place here. Okay, this is actually the place, okay, of that one. For example, you actually put green here as for this vertex or this place, and then make sure that all the connected vertices, okay, or connected vertices to that point should be of different color. So if this is green, the others should not be color green. So if you color this as green, the other points connected to it should not be green, as you can see here. So that's it, we've done with it. Then let's say, for example, you want to color this as yellow. Okay, and then those connected to yellow should not be yellow, so it should be of different color. So that's why this one should be blue. And then you've decided this is blue. Okay, and then for example, that's connected to this, and you color this as yellow also. You can actually use a yellow because this is green, so you use another color here. It cannot be blue because it should be it's connected here, so it cannot be green because it's connected here. It can be yellow, okay, because this yellow here is not connected to this one. So that's all. Then can we actually use green here? No, because there's a green there. So use yellow here? No, so you use blue. So you use blue here, it can be. And then in here, this blue here can be also, you can also use yellow here, okay, because it's only connected to green, okay, and it's not connected to yellow. So this blue can be blue or it can be yellow. You can change it to yellow, just okay, because it's not connected to yellow, it's only connected to green. So this is okay. And then you think of another color, it's here. Let's say, for example, why you use another color here, red? Because we cannot use any more blue because this is already blue. So if you put blue here, cannot be because it's connected here. Can we use yellow? No, because there's yellow there connected to it. Can we use green? No. So we cannot use anymore the yellow, green, and blue. So think of another color, red. And then in here, there's you can use blue, or you can use yellow, or you can use green. Why? It's possible because only red here. So you can use green, yellow, or blue here. So they decided to use blue here. And then how about this one? So you can use red. You can also use green here. Why? Because it's not connected to green. So if you use green, that's yellow. So okay. If this is green, still okay because this is blue. So this red here can also be a green color, but we decided to use red. And then you think of another color here. So since this is red, you can use here green. You can use here yellow because it's not connected to yellow. Both are red here. And then you can also, yeah, yellow, green. Then you can also use blue. So they decided to use blue here. And then those are the colors. You now use those colors to color the map, actual map. Isn't it? There's the name of this vertices a while ago. I named this as A, B, C, D. And then this part should be colored blue. So if that corresponds to this part here, you color it blue. And then this part is corresponds to yellow there. This one is the green. So this one is the green. And then this is the inner blue here. It's here. This is the blue. This is actually the letter F a while ago, and that's blue here. It's here. This is actually, if you still remember, my letter E, and you color it as red. Okay, so that's how to color. So how many different colors do we use here? We have the blue, the yellow, green, and red. So 4. So at most 4. As I said, if it's a planar graph, you may use at least 4. It doesn't mean that if you color a map for the number of countries, let's say for example, if there are 10 places, there will be 10 different colors. No, you may at least you may use at most 4, and there will be no neighboring towns with common color. Okay, so that why there should be different color for neighboring towns, so that you can actually distinguish the boundaries, isn't it? So that's the use. And in here we need to find the minimum number of colors that you need to use. Okay, so this one is another problem. Okay, so there's no color for each part or section of this map here. So there, you need to actually convert it to a graph, to a planar graph, and think of colors to use, and check whether you can use 2 only or 3, or it may be 4 colors. Okay, and that number of color that you use in coloring a map is what we call chromatic number of a graph. It is the minimum number of colors needed to color a graph so that no edge connects vertices of the same color. Okay, that's what we call the chromatic number of graph. And it says here that if the graph is planar, you can actually use at most 4 or less. There are actually graphs that you can only use 2. You may only use 2 colors or 3 colors, up to 4 colors. But if it's not planar graph, you need to maybe use at more than 4. Okay, so that's for the lesson, okay, on planar graph. Okay. Thank you.